Start our study of magnetism today. Can I have your attention, everyone, please? Okay. All right. So, magnetism. We're going to first talk about what we mean by a magnetic field, and then why we think it exists, and then what does a magnetic field do, and then how do you produce a magnetic field? How do you actually calculate a magnetic field? That's ultimately what we want to do over the next couple of chapters. Okay? So magnetism, obviously, we will just summarize hundreds, maybe thousands of years of experiments and efforts and so on, and then just get down to a couple of equations that summarize all these experiments. So you have bar magnets, right? Bar magnets, like this one. And then you can start doing experiments with them. What do? You bring them next to each other, they stick together, and then maybe look at the ends, the poles, the two ends. You will find that, for example, these two ends, they repel each other, and then these two ends, they repel each other. So you need to give them different names. The names are north and south. Could have been plus or minus, but so north and south. And then opposite ends, north will attract south, and south will attract north. Okay. If you try to just isolate the north, let's say this is the north, and you just cut it off, you will get another north and south. Here is a broken magnet, and it has a north, I guess this is north, yeah, and the south. They repel each other. Okay, a broken magnet like that. Then, okay, there's this thing called a magnetic field, and it's really not an electric field, because if I were to put a charge here and it's not moving, it will not experience the force. So this new thing, it can't be explained with gravity, it can't be explained with electricity, so maybe it's its own new thing. So what is it? You give it a name, you name it. It's a magnet, so magnetic field. You need to give it, it's a field, so it needs to have a direction and a magnitude. So we need to first define its direction. So how do we define its direction? It goes as follows. So again, I'm skipping a lot of, there's a lot of history, but so here's a magnet, here's the north, here's the south, and people know about compasses, right? A compass needle also has a north and a south, and the compass needle's north will point toward the north of the earth. So what's the direction of the magnetic field? We will just say it's defined by the direction of the compass needle. So let's bring compass needle next to the magnet, and whatever direction it points, we're just going to say that's the direction of the magnetic field. So for example, if you put that compass needle here, it will point this way. If I put it slightly here, it will point this way. And then if I put it here, it will point this way, and maybe this way. Again, approximate results, and then it points this way. So we can think maybe the magnetic field points like this, and then if you put it on this side, you will find that the magnetic field points in this direction. Okay, so that's the direction of the magnetic field. It will be whatever the direction of the compass needle will be. Now, you also have to give it a symbol, right? And what's the symbol for the magnetic field? If you read through the book or the notes earlier, what do you think?
P as in boy?
Yes. So the symbol for the magnetic field is B. Okay, that's the magnetic field. Again, we will not worry about how it's produced. We'll worry about that in the next chapter. Basically, in summary, moving charges, they produce magnetic fields, or currents, they produce magnetic fields. Okay? So that's the magnetic field. We gave it a symbol. We know its direction. So suppose now I produce a magnetic field in a certain direction. So let's say we have a magnetic field in this direction. Okay? Okay? Let's say somebody somehow produced a magnetic field in this direction. And how do I know it's in this direction? I bring a compass needle, and then if it points in that direction, it is in that direction. Okay? So what we do is we experiment. So you bring a charge. Let's say I bring a plus Q, a positive charge here. And if the charge is at rest, there is no force. The force would be zero. So here is, that's some experiments, right? So if V is equal to zero, the force, the magnetic force, FB, I'll just call it F, then the force on this charge is just going to be zero. For the electric force, remember, it didn't require the charge to be moving. What's the electric force? If you have an electric field, then you put a charge here.
Q times E.
QE, yeah, the charge times the electric field. There is no requirement that it must be moving, but for this one, if it's not moving, it will be zero. Other experiments. So what if the charge moves parallel to the magnetic field or anti-parallel to it? If it makes an angle, if the velocity is angled, it's 0 degrees parallel to the magnetic field, or maybe 180. So if theta is 0 or 180 degrees, so if the charge is moving parallel or anti-parallel, again, the force will just be 0. Okay, measure the force, you get 0. How do you measure force? You measure the acceleration, and then mass times acceleration will be the force. Okay.
Where is that theta?
Theta is the angle that the velocity makes with the magnetic field. So if the velocity is in the same direction as the field, 0. If it's opposite to the field, it will be 180. Okay. That's that. Then you start, okay, this way doesn't work, this way there is no force. What if I orient it at a different angle? What if the velocity is this way? Let's say the velocity is this way, the magnetic field is in this direction, right? That's V. And so maybe they make this angle. Then the force is actually not 0. Okay? So if the angle is not 0 and it's not 180, the force will just not be 0. Okay, keep changing the angle, the force gets larger and larger and larger, and at 90 degrees, you get maximum force. The force is maximum. So, more experiments. So if theta is 90 degrees, the force is maximum. If the angle is 90 degrees, the force, this magnetic force, reaches some maximum value. Okay. Now, we will use this maximum value of the force to define the magnitude of the field. How much is the magnetic field? Well, magnetic field's magnitude is this. Is the maximum force divided by the magnitude of the charge times the speed. I put absolute value for the charge because the charge can be plus or minus. So this is the magnitude of the field, so I get a positive sign. Make sense? So that's how you define the magnitude of the magnetic field. So now this leads to the units. What are the units of the magnetic field?
Newtons over meters, column,
Let's write it down. I hear newtons over what? Coulombs?
meters.
Meters per second, yeah. And then if you know this, you can say a coulomb per second is an ampere. And so it would be newtons divided by ampere meters. So it would be newtons and ampere meters, yes. And it is 1 Tesla. Yes. T for Tesla. Okay? So the unit is the Tesla. Let's move this one away.
No, we got the
Oh, you guys are now you
Now, how much is a Tesla? Is that a lot or a little?
A little?
Well,
A lot.
actually a lot.
It's a cost.
It's a lot. It's a strong magnetic field. So let's see, let's compare, right? Strong, because it's kind of subjective, right? If you say something is strong or weak, compared to what? So, so let's compare it to, the most familiar example is the Earth's magnetic field. So let's talk a little bit more about units. 1 Tesla is equal to 10 to the 4 Gauss. G. G for Gauss. 10 to the 4 Gauss. It's just another unit. The SI unit, the SI unit is the Tesla. So, for example, the Earth's field, B Earth, is about, approximately, right? About 0.5 of a Gauss, or 5 times 10 to the minus 5 of Tesla. It's not that big. And I mentioned in other class, do you think a bar magnet is stronger or Earth's field? The magnetic field due to a bar magnet is stronger, or the Earth's
Stronger.
field is stronger?
Bar magnet.
Bar magnet is stronger because if you put a compass needle next to a bar magnet, it will point in the direction of the bar magnet, not the Earth.
Yeah.
Yeah. So so for a, it says here a refrigerator magnet, the one you stick on your refrigerator, it's 0.01 Tesla. So I would not write. I would just say. So for refrigerator magnets, it's 0.01 Tesla. Yeah.
So when they were hucking stuff up into space, do they have to take into account the magnetic field for orbit, or is it negligible? Like, I'm trying to gauge how.
You have basically everything is kind of neutral, right? Yeah. So you will not be affected by the magnetic field that much. Yeah. Right. You need the magnetic force would be proportional to the product QVB. Yeah, and so the force would just be 0. And so on. An industrial magnet, it says here 0.1 Tesla, and then you can produce stronger magnetic fields, 10 Teslas, 20, 100, 200 Teslas. Yes?
I'm confused on how you got that equation rules of max.
We were saying the definition of the magnetic field, of the magnitude, is whatever this maximum force is divided by QB.
And that's true for any magnitude of a magnetic field, even when
Yes.
max isn't applicable, like even when it's not happening. Like-
So we start with point charges, and then we move those charges in different directions. And then at certain direction, the force will be maximum. And whatever that maximum force is, divided by the charge and the speed,
Oh.
is the
So
maximum.
you say the magnetic field is constant every time that you're putting the force.
At that point in space, yes.
Okay.
Yeah. So the magnetic field will have a certain value at different points in space. So pick a point, and you ask, what's the magnitude of the field at that point? And it will be that much. What's the direction for the compass needle? You will know the direction, and now you know magnitude and direction, so you know the magnetic field. Yeah.
How do you find F is equals to 0 when theta is 0 or 180?
How do you find that?
Yeah. Do you
You
involve
measure.
any sign?
We didn't get to that yet. All this is supposedly
Oh.
an experiment. You're doing an experiment, and you find these are the results of the experiment.
Oh, okay.
We didn't do that, but I'm just summarizing what the experiments say. And then at the end, we need to come up with a law that describes all of these experiments. And I will mention that law right now. So that law says this. The magnetic force, FB, for magnetic force, not electric force now, is equal to the charge, the charge, times the velocity of that charge, cross product with the magnetic field. That's the magnetic force. Where does this law come from? Many experiments, and this is the summary of all those experiments. Okay. the magnitude of a cross product, let me put here FB, the magnitude is just Q, or the absolute value of Q. Speed times B times the sine of the angle between the magnetic field and FB. So let me write it. So here is B, let's say, and maybe B is this way, and this is the angle between them. So notice if theta is 0, sine 0 is 0. So you get 0 force. If theta is 180, sine of 180 is again 0, and you get 0 force. If theta is 90, the sine is 1, so you get the maximum force. If theta is something else, then the force will be something else.
How does it become a scalar above or cross product when we use vectors?
Yeah, you get a vector, and the magnitude of that vector is
Okay.
yes, the cross product will give you another vector. Yes, not the dot. So that is that. Now, what's the direction? How do you compute cross products? So let me write down some cross products. So let's say here is I hat, here is J hat. The cross product of I hat and J hat is, you use your right hand, yeah. There is the right hand rule. It says, I hope everybody remembers that rule from mechanics or from count 3. So you should remember it, and if you forget it, make sure you do it. Yeah, oh yeah, and I see this, and I see this, and I might see something else. But whatever rule you do, just learn one of them, and then make sure you know it. Don't learn like 5 rules and then forget, one to apply them. So you just need to know one. Okay? So the one I remember is to curl my fingers from I. If I want the cross product of I to J, I orient my fingers toward I. Now, I can orient my fingers toward I this way, or this way, or this way. All of them, my fingers are pointing in the I hat direction. Which one do I choose? Well, I choose the one when I curl my fingers, they will point toward J hat. So it must be this way. Okay? And then my thumb will point outside of the board. So in this case, it's K hat. So I hat cross J hat is K. Now, you need to also remember that I hat crossed with, or this way, J hat crossed with I hat will be what?
Negative K.
Yeah, when you reverse the order, you get a minus. Okay. So J hat cross I hat is the reverse of I hat cross J hat. So minus K hat. On the other hand, if you do I hat cross I hat, it's the same as J hat cross with J hat, and it's the same as K hat cross with K hat, and which is what? Just 0, right? Just 0. Because they are parallel to each other. I hat is parallel to itself. So you get 0. The sign is 0, right? Cross product's magnitude is the product of magnitudes times the sine of the angle. They are parallel, but the sign is just 0. That's that. Now, let me ask you this one. Let's say this is V, and let's say this is E. In what direction is the force? And let's say the charge is positive. So V cross B is in what direction?
K. Towards us.
Yeah, so here is V, that's B, so I need to curl my fingers from B to B, and I get that. Yeah. So it would be this way. So the force would be out of the board. Now, how do we symbolize out of the board? A circle with a dot, right? This is the V cross B. That's the direction. Up. Yeah.
Can you symbolize into the board?
Let's do that. Yeah. So you wouldn't forget, the dot is like an arrow coming towards you, and you're looking at the tip. So you just see a dot. And now if it's going away from you, meaning into the board, it will be like an X, maybe an X with a circle. So, yeah, that's the back. Yeah. So that's that. So let's say the magnetic field is N. Okay, this is the magnetic field. So let's say this is V. Let's say here is V. So in what direction would the force be? In this case,
Down.
down. Do your cross
Oh.
product.
Up. It's up, going up.
Into? It could not be into. The magnetic field is into.
It's going up.
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 Yeah, it's going up. It is up. Yeah. The magnetic field is in. The V is this way. So curl your fingers from V to B, and the force will be upward. Okay. The force will be upward. Is that clear or not?
Can you explain again, please?
Here is the magnetic field is in, right?
Yes.
This is the V.
Okay.
So the force has to be up.
Oh.
Because you need to curl. So again, this is V, right? That's V. I need to curl my fingers from V towards V, and it's up. So the force is upward.
Oh.
And by the way, this assumes the charge is positive. Okay, this assumes the charge is positive. Okay. What if the charge is negative? It would be just the reverse, because you would have a minus sign in front.
Yeah.
So you would do the cross product and then just put a minus sign in. Okay. Yeah, and so on. Let me maybe do one more. Let's do one more. Let's say now here's. Let's do one more. Again, let's assume the charge is positive, and let's say now this dot is the speed, or the velocity. Let's say the velocity is towards you. Okay. So this dot is what? The speed, the velocity, right? The object is coming towards you, and it's a positive object. Let's say. And let's suppose the magnetic field is up. So in what direction is the force?
Right. To the right.
To the right or to the left?
To the
Make
right.
sure you use your right hand. Yes, it would be to the right.
To the right.
Oh, yeah, your left. Yeah. Yeah. Okay, sorry. Yeah. Yeah, the force. Yeah, I was thinking from my perspective. Yeah, that's my right. Okay. Okay. But we agree on that?
Feed B.
Yeah.
This
So,
right.
well, let's. This is B. And that's B, right? So curl your fingers from B to B, B to B. Yeah. Whatever the direction is, okay? Your left.
Oh, feed B.
Okay.
I don't know what's
Yeah, it's hard to do.
You have to do this.
sometimes.
You have to do this. Yes, he's facing towards us. You have to turn around like he is.
Yeah, well, it's easier sometimes.
I used to know how to do
It's
this.
all like his left.
It's
You need a
confusing.
mirror.
See, I
Sometimes it's easier if it's, you have to twist your arms and stuff like that. So here's what you do. Just do B cross B instead of B cross B.
It's like,
So here's B, here's B. If I do B cross B, I get this way. But B cross B is the negative of that, so it will be this way. Which is yeah, so just properties of cross products. If you have vector, let's say vector A crossed with vector C, it's equal to minus the vector C crossed with vector A. That's a property of cross product, right?
One more.
We'll have more on the worksheet of these. Huh? We'll do more on the, yes, please.
The what?
Up to you. Yeah, up to you. It's usually a simple cross product.
Terus satu
Let's see. So now I would like to discuss, so these are point charges moving in a magnetic field. What if I have a current carrying wire a wire that has current and it's in a magnetic field. What force would it experience?
Double.
Oh, here it is. Magnetic force on a current carrying wire, right? So suppose I have a current carrying wire and it's in a magnetic field, right? So let's say here's the current, I. That's the current. It's a wire, it has current, and it's in a magnetic field. Let's say the magnetic field is in this direction. Here's B, it's to the right. Let's say that's the magnetic, it's to the right. Good? And the question is, what's the magnetic force on this current carrying wire? The magnetic field is to the right, so I will just draw it once. So when I draw one arrow, it just means there is magnetic field everywhere and it's to the right. Now, how do you produce a magnetic field that's to the right? We will worry about that later. For now, we have a magnetic field to the right. Remember, like electric field? We say electric field that points this way. How do you produce it? Infinite sheets, right? We will learn how this one is produced. But for now, let's just say there is a magnetic field and it's to the right. We don't need to worry about how it's produced. And the question is, what's the total magnetic force on this segment? So the idea is break this segment into many little segments. So here's, because the current carrying wire, there are charges, right, that are moving, DQs, and they are moving. So let's take a little DQ here. Let me draw it with red. There is a charge, and it's moving in this direction, right? So I have this. The force on just that little piece is dF, and it's equal to dQ, the amount of charge here, and it's the speed with which the charge is moving crossed with the magnetic. Cross product with the magnetic. That's speed. This speed is the drift speed, right, in the wire? Like this. The charges that are moving in the wire, it's called the drift speed. Right? Not that we need it, but just that's what we call it. Now, velocity is the rate of change of position, right? So let's say this is the direction ds. Ds. So ds dt is the velocity. So let me dq is ds dt crossed with the magnetic field. I would have dq dt ds crossed with magnetic field. What's dq dt? It's the current. Now, that's the force on just that one little segment. So if I want the total force, I need to integrate along this current wire. So if I want the total force, I need to integrate. I need to sum it up. So meaning this. So if I want total force, the current is constant. Let's say. Yeah.
How would the current be constant? Is it just a constant current density?
So the current in a wire is usually, let's say, 1 amp or half an amp or something like that. So it's like we're assuming a steady current. What? Yes. Yes. So let's think about what's going on there. So how do we evaluate this integral? Technically, you will have to do the integral. But it simplifies if the magnetic field is constant, uniform. If the magnetic field is uniform, we can just pull it out of the integral. So it will be, we need to keep the vectors. So if the magnetic field is uniform, I'll put here this equality, B is constant. So it reduces to this, I, and then ds. Cos 2t. Yes? If I have vectors A, like vector 1, vector 2, vector 3, vector 4, the sum of all those vectors times another vector. So I can sum up the vectors and then multiply, or I can multiply each vector and then find the sum. The product of the sum or the sum of the product. So then separate this. The magnetic field is constant. Now, what is this? The integral of ds. The sum of all these ds segments. So here's the ds. Let me draw it. Here's a ds. Here's another ds. Here's another ds. And this one. And this one. This one. This one. And this one. What's the sum of all these little vectors graphically? It is S or
Is it the
but what does it
current?
represent?
The current? Or current? The current?
The curve?
The current. Is it the
The current? No, this is a segment.
Oh, okay.
Would
Yeah.
that be the arc length?
The arc length
Needs to be the length of the line.
of the, okay, almost. Not quite though. Yeah. Remember, are we adding the s's, their magnitudes? If we added their magnitudes, yeah, it would be the arc length. But we're not adding the magnitudes. We're adding, yes. Liam? Yes, it would be this. It's this line. The it's gonna be this. Yes. Okay.
What do you call that one?
Huh?
What do
You can call it the line secant because
Oh.
it connects the endpoints. So it's just going to be this. If the magnetic field is constant, it's going to be I and then L crossed with B. Generally, the magnetic field will be uniform, and so generally speaking, we would have this equation here. Just like, think about this one. Let's say I have a vector A, and I add to it a vector C. I'm trying to avoid B. And I add a vector D. What's the total? A plus C plus D.
Straight
It's
line.
this vector, yeah. Well, maybe vector F. No, F is already used. Vector E. Okay. That's good. Now, what if it's a closed loop? If D is uniform, and we have a closed loop, what do we get for the force? Well, the force would be this. I'm going to rewrite this one here. It will be I ds plus B, like so, right? But I want a closed loop, so I'm going to draw it closed. So what's that?
Zero?
Yes. That would just be the displacement. The sum of all the little ds is going to be the displacement, and that's zero. It's a closed loop. We come back to the same position. So this is going to be zero. So the force on a closed loop is going to be zero, assuming the magnetic field is uniform. Okay. So we're going to do an example.
Professor.
Yeah.
So L is a factor?
Yes, L is a vector. And L is the magnitude of it's this length.
But L doesn't have direction.
It does. It points from here to here.
Oh.
It does have a direction. Let's try this example, maybe clarifies it. we're going to consider a closed loop in a uniform magnetic field. So we know what the net force should be. What should it be? 0. So here is a loop. Here is a closed loop. Here is the x direction. Here is the y direction. And here is the loop. It's a semicircle. So our closed loop is this. So the current runs this way. Right, that's the current. So the current is going around. And let's say if the circle has radius r, this is minus r, and this is r, right? Minus r. Radius of the circle is r. And our goal is to find the force on the straight segment and the force on the curved segment. Assuming, well, I need to tell you where the magnetic field is pointing, right? In this case, there is no force, there is no magnetic field. So in what direction is the magnetic field? Let's say the magnetic field points up. Magnetic field is uniform and it's up. This is B. So it's just B and then J hat, okay? B, J. Constant J. That's the magnetic field. So find the force on the straight segment and then the force on the semicircle. So if I say what's the total force, you should say how much?
0.
0. It's a closed loop. It should be 0. Let me ask you, on the straight segment, in what direction is the force? Is the magnetic force? I hat. The current points in the I hat direction, yeah, in this one, but the force is not I hat. That way? Towards you? V cross, yes, yeah, it would be towards you, good. It would be towards you.
Wait,
Yeah.
so the right hand rule also applies for I, B, and F?
Yes, because what is I? It's little positive charges moving, right? So think about every positive charge. So you have a dq, right? Take a little charge here. You'll have a little plus charge moving to the right with certain speed v. And then the magnetic field is up, so V cross V. Jack? Good?
Oh yeah, I was just thinking about how it's gonna be on the curve.
Okay, and the curve will be into the board. We'll figure it out. We'll figure it out. We're going to do it. So let's find it on the straight segment and then find it on the curve. Yeah.
Wait, so are we finding two forces? The force of magnetic field and the one that's on the current carrying wire?
No, we're trying to find the magnetic force on this segment and then the magnetic field force on this segment. So find the magnetic force on the straight segment, find the magnetic force on the curve, on the semicircle, and I know that the sum of these two magnetic forces needs to be 0. And I'm going to double check that.
Oh,
So let me write. So on the straight segment, I'm going to call it F1, and on the